All right, so welcome everybody to Hoon School Live Lesson 4. I'm going to begin the lesson with some short wrap-up of last lesson. So I'm going to talk briefly about style first. So far, as you might have noticed on the homeworks, we've been spending a lot of time on converting between sugar form, wide form, and tall form. And why do we spend the time on this? So production Hoon code is usually going to use all of these different forms. And it's going to be really helpful for you guys to know how to convert between them. So for example, if I just have a cell of two values, like something like this, like obviously you just write it in the sugar syntax, right? That's easier to read, easier to write. Or even like something a bit more complicated like that, you just use this cell notation, right? But what if I want to make a cell with a complex expression as one of its sub-arguments? So consider this code, which you may recall from last lesson. So here we are defining a new type union called reptile, which is a union of sen snake, sen lizard, and sen crocodile. We're making a new instance of that called R, and it has a value sen snake. And then we're doing a switch on it, right? So suppose we wanted to return a cell of R and the result of passing R to the switch statement, like a cell of sen snake and the text, I'm a snake. In this case, since this is in tall form, you can't put this inside the cell notation, right? Because tall can't go inside in regular form. So to get the output we want, we have to use the rune for Cohort like this. And I'll paste this code in the chat for you guys. And if you would like to run that in your dojo, you can see that it will return the cell of sen snake and I'm a snake, because it's here we're saying make a cell of R and the result of this switch statement. Does that make sense? For one of your homework problems, I had you guys desugar a statement like this. So I pasted it in the chat. Sen hep, or sorry, ket hep, num equals pat ud, text equals pat t. So this is a type definition, and this is a value, right? And I had you guys desugar this. In practice, you'd never like write the fully tall form version of this. But the reason we go over this in Hoon School is to understand that these actually desugar to different things. And by spending the time in Hoon School, it'll help you avoid running into bugs when you're out in the wild. So as you may know, Hoon differentiates between a single space, which we call an ace, and two or more spaces, which we call a gap. When we use runes in tall form, each child is separated by a gap, right? Each child is separated by two or more spaces. So technically, any sort of formatting where you separate the children by two or more spaces in these cases is valid. But there's generally a standard, like nicely formatted way to write it. And as we are beginning to write longer and more complex code examples like this, it's good to adhere to proper style guidelines. So it would technically be okay to write our reptile switch statement all on one line like this. So it's even hard to read, but basically I just made this whole switch statement on one line. And that works, but this is hard to read, right? So really the proper way to write it is going to look like this with this formatting. And if you're ever confused, you can always just go to the docs, the developers.urbit.org, type in some rune, and then you can see it'll tell you this is the proper style to write it, it is another proper style to write it, and so on. So yeah. All right. So there's another useful shorthand we can learn. So suppose you have defined a mold like reptile and you want to declare an instance of it, and you don't want to just like use like a new name, because you're just making names all over the place, right? So what you can do is you can use this syntax right here. So you have tisfaz equals reptile send snake. And what this does is this declares an instance of this mold reptile that also has a face reptile. And that means in this code right here, in the switch statement, this reptile is going to refer to this. It's not going to refer to the mold definition. So that's a really convenient bit of syntax. I'll paste that in the chat if you'd like to try it. And I can just directly show you. So if I do this, that's the mold definition. This is the instance definition. We're saying equals reptile send snake. If I just return reptile, then it returns this send snake rather than returning the mold. But if I did the same thing, kept those lines the same, and then I did this ket reptile, if you recall this notation, it says skip the first match and get the second match in the tree. Then this is going to return the mold, and the mold is going to take a while to return because it has a whole context of the dojo, so it's spinning. All right, any questions on any of that? Yeah, we're just learning this new like little syntax right here, just declaring an instance of a type. All right, so far we've been using library gates like add, sub, mold, div, etc. for non-negative integers, right? For pat UDs or atoms. We have all these for floating point numbers as well. So let me exit this because there we go. So the way you you operate on floating point numbers is use the RS library, and it just works like this. So you do add col RS. So this is specifying you're getting add from the RS library. And here's two floating point numbers, -1.234 and 5.678. And there's your result. You have division as well. You have comparison. And there's even the square root function. So yeah, that's just like a neat little thing to remember. You have all these floating point abilities. But yeah, let's get into the big topic for today, which is going to be lists. So recall from last lecture that we made cell types with the buckhole rune, this rune right here, right? And if we make a cell type with that rune, it expects a certain fixed number of children, right? So I can use the buckhole rune to make a structure that's a cell of 2 pat UDs, right? And that won't fit a cell that's 3 numbers. So I made this type, which is a cell of pat UD, and I use this ket hep to try and force this 1, 2, 3 into that mold, and it's going to crash because this has 3 things and this specified 2 things. And likewise, something that's a cell of 3 numbers is not going to fit something that's 2 numbers, right? So if we make a 3 nums type with 3 entries, and we try to force this cell of 1, 2 to fit to it, we're going to get a nest fail. However, in Hoon, like you'll need data types that don't know in advance how many entries they have, right? So this is fulfilled by list, and a list is the same structure as is a data type with the same type of thing in all the entries and a variable. So let's try a simple example of making a list. And I'll paste this code in the chat for you guys. So what's going on here? Let's dissect it bit by bit. Let's look at what's going on the right-hand side. So this, if you may recall, is structured as this rightward branching cell of cells. So the underlying data structure is going to be a cell of 5 in sig, then a cell of 4 in that, and then a cell of 3 in that, and 2 in that. and so on. And then that sugars to this representation right here. So that's what's going on here. And the name for this is a null terminated tuple because it's a tuple that ends with a null, this sig character. When we have a null terminated tuple, there's another sugar syntax we can use, which is just like this. We pull that sig out and we put it at the front, and that just helps us read it. Instead of having to visually scroll all the way to the end, the sig in front tells us what kind of structure this is, and it differentiates it from the cell. Right, so, and if we put this in the dojo, we'll see that it's the same thing, it's just a different way to write it. Oops. If we replace this sig at the end with another number, this structure can't be a list. This is just a 6 tuple, because Hoon doesn't know that. Hoon uses that sig at the end to understand that it's a list, basically. So what else can be a list? We can just have sig that can actually be cast to the empty list. You can have a cell of 1 in sig, right, which is a tree like this. You have a cell of 1 and the cell of 2 in sig, which is a tree like this, and so on and so forth, right? However, the Hoon compiler doesn't necessarily know that all of these structures are lists. Just because something is a tuple with a sig at the end doesn't necessarily mean it's a list. Like, for example, you could, like, for some reason, want the cell of sig and sig, or like a triple of sig, 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 for whatever reason, right? And you don't want these to automatically be understood as lists. So how Hoon works is, when you have something that's structured like this, it can be a list, but then you have to cast it to a list to explicitly make it be understood as so. And that's what we're doing. That's exactly what we're doing in this code here. So I'll type that in the chat again. So looking at this code, we should notice a rune we're familiar with, right? There's a senhep right here. And can anyone tell me what that implies about what's going on in this code? What does the senhep imply? Yes, exactly. So yes, list, the term list in Hoon is actually a gate. And precisely what it is it's a mold maker gate. So list is a gate that takes as input a mold, like PatUD, and it returns a mold, which is a list of the input mold. In most production Hoon code, you'll see the syntax like this, with these parentheses around the list PatUD. But it's important to know that these parentheses actually desugar to this senhep. It's a gate call. It's not just like formatted like this for whatever reason, but it means that we're calling the gate list on PatUD. There's other mold maker gates that we will learn in the rest of the course, such as set, which takes a type and creates a set of that type, and map, which will take 2 types and create a map between one type and another type, and so on. But the only one we need to work with for now is just list. So we can use this mold maker list with any type, including custom ones that we define. So recall that we define this type union reptile as a union of snake, lizard, and crocodile. And we can even just make a list of reptiles. We call the gate list on the type reptile, and we cast this thing to that list type. And I'll paste that in the chat for you guys. And you can also write this in the sugar syntax version, which you'll probably see more often in production Hoon code, which is just parentheses list reptile, just like that. I'll paste that too. And we can even use it with more complex types. Like if you'll recall, we made a reptile tracker type, which was a cell of species equals reptile and meals equals PAT-UD. And you can make a list of reptile trackers, just like this. So we have a list with each entry is crocodile 2, snake 3, lizard 5. And the sugar syntax will look like this. Right, we just sugared this list reptile tracker. We can even make lists of other lists. So what's going on here? Let's make this bigger. So we have kedhep, senhep list on pat-t, and then senhep list on that. And then that means what this is a list of lists of pat-t. So we can see each inner thing is a list. And then we have 3 of them and then a sig. So and it comes out like that. And the much easier to read sugar syntax is here. So we have list pat-t inside of a list. So this is a list of text. Any questions so far? All right, so I have a question for you guys. If lists are represented as a binary tree like this, is it faster to add something to the head of the list or the tail of the list? Yes. Great comprehension, guys. It's much faster to add something to the head of the list. Because for the tail, we have to navigate all the way to the end to add something. Whereas for the head, we can just append it to the head like this. And I'll show you exactly what the syntax for that is. So if you define a list, so I define my list of PAT-UDs as 2, 3, 4, sig, then I can just add something to the head of it with this Cohort rune, right? We're making a cell of 1 and my list. And if we recall, this tis dot rune is saying, take my list, something in the subject, right? We defined it here, and then modify it to be this new value. So we're taking my list, which is 2, 3, 4 sig, and we're changing it to be the cell of 1 and the old my list. So if we do that and return my list, we get the cell, we get the list 1, 2, 3, 4. So I will paste that code in the chat for you guys. This is kind of interesting, right? And you can also do this with the cell notation. So define my list and change my list to be a cell of 1 and my list, and then return my list and the same thing. So I'll paste that too. So yeah, that just corresponds visually to this operation right here. Any questions on that? All right. So based on our list definition, right? Any empty or null list is just sig, right? Or in particular, sig cast to a list. Hoon has a special type for lists that you know are not empty or null. And it's called lest, like with an E, L-E-S-T. For example, like I can cast this to a list. I can cast this just sig to a list. I can cast this to a lest, but I cannot cast just sig to a lest because lest is a list that's not null. So I get a failure there. If you can prove to the compiler that your list is a non-null list, there's one more interesting thing you can do with it. So if it knows it's a list, so I have A defined here as a list of pat_ud, then I can do I.A and get 1. And in this case, I is a face which is attached to the head of the list, which is just the value 1. And I can also grab the tail of the list. And if you think about this binary tree notation, if the head is just this value, then the tail is this whole thing, which is another list, right? So I define A as before. And if I do T.A, then I get this remainder list 2, 3, 4, 5. So that's pretty useful, right? And if this is just a regular list, if the compiler only knows it's a list, then I can't do that. I'll get a failure. Let me give you guys that code. There's another way that you can make sure a list is non-null to the compiler. So let's look at this code here. So we assign A to a list of pat_ud, and then we have this rune whatsig. And if we remember whatsig from the last lesson, it's a branching rune, right? So whatsig, its first child is something. Second child is what you do if this first child evaluates to sig, and third child is what you do otherwise. So basically what this code is saying, if A is just null, then do zap. And what zap we haven't learned yet, but basically all that does is that just crashes your expression. So if you type zap in the dojo, you'll just get a Hoon expression failed because it just crashes. So what this is saying is if A is just sig, then crash. Otherwise, do I.A. And if you do this, then this will also prove to your compiler that A is not just null. And then you can use I.A or you can use T.A. I'll paste that in the chat for you guys. And if I get rid of that line, if I get rid of that non-null check, then I'll get a crash. And this is something that people run into sometimes, a bug that people run into working with lists. So it's good to remember that this is why you can't use this I and T face. But if you check that it's null and make sure it's not, then you can. Are there any questions on that? All right. So why would we store data as lists? Doing so gives us access to a lot of really powerful tools. Hoon comes with a really big library of gates to manipulate and make use of lists. I'll drop a link in the chat right now. And this link is the page for all the standard library gates for lists. So we're not going to go through all of these, but let's go through some simple examples. So we have this gate called flop. It just takes a list and reverses it. We have a gate called gulf, which takes two non-negative integers and returns the list of all the numbers between the first number and the second number. So gulf 520 gave us 5, 6, 7, 8, 9, all the way through 20. Lent just returns the length of a list. It's pretty straightforward. There's one called limo, which is kind of interesting. So limo is basically like casting a list with kethep to the structure of a list. So basically senhep limo of this is essentially equivalent to doing this kethep list pat-ud of this. The advantage is limo doesn't need to, you don't need to feed limo like the inner type. You can just use limo. There's one called snag, which can get the element at a certain index. So let me type this code in the chat. Oops. Why did I click on podcast? So snag needs to know the input is a list. So we do limo to force this to a shape of a list. And if I snag the thing at the 3 index, it should return rabbit because it starts from 0. So this is 0, 1, 2, 3. And we get rabbit, right? We could have also done it with casting it with this tick notation. There's one called snap, which instead of grabbing the thing at an index, you can replace the thing at an index with another thing. So snap this list, index 3, make it into squirrel. And then we get dog, cat, mouse, squirrel, deer instead of rabbit. So we can sort lists as well. What if the list is shorter? Sorry, what do you mean by that? Oh, so let's try it. Like if this index is out of range. Is that what you mean?
Yep.
Yeah, let's try that. And interestingly, it just seems to add it to the end. Yeah, so if that number exceeds the size of the list, it just adds it to the end. Interesting.
And how about if you want to take it?
Sorry?
Snag.
Oh, snag. Yeah, let's try that. Snag 300. And then you get a failure. That's kind of interesting. Are there negative indices? No, there are not negative indices because this argument is a pat-ud, and pat-ud doesn't have a negative representation. So, yep. Are there any performance gotchas you need to watch out for when using lists? There are, and we will discuss those more when we start learning about recursion in Hoon. But for now, we can save that question for later. All right, so we can also sort lists. So there's a library function called sort. It takes as input a list and a gate. And that gate should take as input 2 elements of the list and either return a send.y or a send.n. And the standard library gate, LTH, satisfies that for us, right? Because if you recall, LTH takes 2 pat-uds or 2 atoms and just returns send.y if the first one is or send.n, right? So if we call sort on this list and use LTH, then it'll sort them from smallest to largest. And we can also use sort with GTH as an input. And what that'll do is that'll sort them in the opposite direction. And this, you can do this with any sort of comparison and any sort of value. So it's really flexible like that. It doesn't have to be numbers, it can be text, it can be whatever, as long as you have a function that'll return a send.y or a send.n. So yeah. You can concatenate 2 lists with weld. So weld 1, 2, and 3, 4, 5 gives you 1, 2, 3, 4, 5. Now here's a really interesting one. So there's a gate called roll, and I'm going to show you some examples of what roll does, and maybe you can figure out what it's doing. So roll, limo, 1111 add. What does that do? It returns 4. Roll limo 1111 mul 1. And roll limo 1234 mul 24. So yeah, what do you guys think is going on here? Yep. I think it's the equivalent of reduce in another language. But yeah, basically, it takes as input a list and a gate, and that gate should take as input something of type of that list, 2 things of type of that list, and output something of type of that list. So that works for add, right? Add takes 2 atoms and returns an atom, right? So what it'll do, it'll do add 1 1, get 2, then add 2 1, get 3, add 3 1, get 4, and return 4. And here it's going to be multiplying 1 by 2, getting 2, multiplying 2 by 3, getting 6, multiplying 6 by 4, and then getting 24. So that's pretty cool, right? There's another interesting one called turn, and this may also map to something that you're familiar with from another language. So we have send less turn list and then dec, which is just the function or gate that takes a atom and decrements it, right? So what's going to happen here? It went from 2 3 4 5 6 to 1 2 3 4 5. Yep, exactly. Great answers. So turn is just going to take this gate, apply it to every member of the gate, and then return the new one, or every member of the list and return the new one. And we don't even have to use predefined gates here, right? We can write our own. We'll learn how to write gates in a forthcoming lesson, but for now we can try some examples. So let's try this. Paste this in the chat. So what am I doing? I defined a new gate called mul5, which just takes a number and multiplies it by 5. So we don't have to worry about that for now. But then if we turn 1 2 3 4 5 with mul5, then we get 5 10 15 20 25. And turn doesn't even need to preserve types, so we can use this with a gate that transforms the types. Here we've defined a new gate called num to ship, which just converts the number to a ship ID. We can turn this list of 1 2 3 4 5 with num to ship, and then we get Nick, Bud, West, Seth, pair. All right, so that brings us to the conclusion of the section on lists. Are there any questions so far? Okay. So if there's no questions, we can move on to the next big section, which is going to be working with text. So, so far, we've learned the PAT-T aura, right? So it's just single quotes, you have some text, and it's like that. And we call these a chord. And we also learned the PAT-TAS aura, right? And that's something that starts with a sen, and then it's a value and it's also a type, right? We've been working with this. And if you recall the nesting properties, but just by the names of these, you can tell that PAT-TAS nests under PAT-T, right? So there's another one we haven't learned yet. It's called a not. So this one kind of sits between a chord and a term. So a chord is UTF-8 text. It's encoded as a single atom, and it basically permits any text symbol you can encounter on the internet, right? A not permits only ASCII, so like all the standard keyboard symbols, and it's used for system labels like URLs and file paths. And the term, which we've learned before, it permits only lowercase ASCII PEP and the numbers 0 through 9, and it's both a value and its own type. So these are the three ways that we can represent text in Hoon as atoms. We can make sure that some text is valid as a certain aura. So how we do this is we use a gate called sane. So what's going on here? We're defining a new gate. And what that is the result of calling the gate sane on sen TA. So sane is going to take an aura represented as a, yes, sanity check. Represented as not with the pat in front, but with the sen in front. So represented as a term. That builds a gate. And then we use that gate on a text and it'll return a yes or no, whether that text is allowed. So that's not allowed as a TA. We can use this in the sugar syntax. That's more readable, right? And probably the fastest way to write this is just like this, right? So here we're building a gate by calling sane on sen TA, and here we're using it on the text angstrom. So suppose you're building an Urbit app and you have some data that's an atom and you'd like to send it to the front end to display, right? You can convert any value in Hoon to a chord by using the gate Scott. So type this in the chat. So we're taking the PAT-P sample palnet, and along with the aura information sen-P, we're passing those to Scott. And then we're taking the result and we're casting it to a PAT-T. And then we get sample palnet represented as a PAT-T. You can also exclude this as well, but I think what this does, this represents it as a PAT-TA. So that's what this casting is doing. The sugar syntax for this, the shorter way to write this is probably just like this. Scott, sen-P, sample palnet. And you can also do it with a hexadecimal. You can do this with any sort of atom. So suppose you have a web app and some user is inputting something and you want that to make a change in your database, right? You can convert chords to atoms as well. So you can go one way and also go up. So the interestingly named gate is Slav. So it's Slav sen-P, this chord, and then we'll actually get it as a raw atom. So what we have to do is cast that back to a PAT-P, and then we'll get the actual PAT-P value, sample palm. So I'll paste that in the chat for you guys. And here's the sugar syntax way to write it. So cast to PAT-P, Slav sen-P, sample palmet. So what happens if we enter something nonsensical here that doesn't work as a PAT-P? Then we get a failure, right? Because that won't fit that aura. All right, any questions on that? Okay, so besides these three ways, so PAT-T, PAT-TA, PAT-TAS, which all represent text as atoms, there's one more possible representation of text in Hoon. You can represent text as a list, which is really powerful because it gives you access to all the list manipulation tools while working on text. In particular, what's called a tape is a list PAT-TV. So let's try to understand this a little bit. So So basically, we're calling the gate list on the aura pat-td. What this means is that this is something of aura pat-t, but only limited to 8 bits. So that's what this D means. This just means we're putting a constant size limit on it. And it's a list of those things. So we're representing this tape as double quotes. So whenever you put text in double quotes, that's going to be a tape. It's going to be a list pat-td, not a pat-t. So any of these, and a list is, or sorry, a tape is a very flexible data structure. So, and basically anything that you can represent as a pat-t is also possible as a tape. And you can also just use the word tape. This basically signifies list pat-td. You can convert directly between chords and tapes. Remember, chords being the name for pat-t and tape being list pat-td. The gates you use for that are crip, which you can remember as chord rip. So you're ripping something to a chord. And see, we turn that from this double quote tape to a single quote chord. And trip. So you can remember trip as tape rip. We're taking a chord and making it into a tape. So why would you do this? Why do we have these separate representations and converting back and forth between them? The reason is, as you mentioned, tapes are easier to work with than chords. They are lists internally. You can use all the list manipulation on them. However, tapes use about 6 times as much storage than chords do because they're stored in the list. So a common practice when working with Hoon is to store text data in a chord, convert it to a tape, do processing on it, and then convert it back to a chord. So that's why these crip and trip are useful. You can convert an atom of any aura to a tape. Recall that we could convert any aura to a chord, just the same thing for tape. And we use this gate called the scow. So it's pretty straightforward. And there's a couple of more useful tape utilities. So we have a gate called cuss, which can take a tape and make all the letters uppercase. So just like that. And there's also one called cas, which takes a tape and makes all the letters lowercase. We have one called trim, which what it does is takes a tape and it splits it at some point. So we're saying trim this tape at the point 26, and we're going to get a cell of two tapes. So that's pretty useful. And we have all these list functions that we can access. So here's something cool we can do. So we can use this gate called find. We're looking for the sublist needle in this text, and it'll tell us the index where it found the needle. That's pretty cool, right? You can use flop on a tape to reverse it. Remember, this was a list function, a list gate that we just learned. Remember, we learned weld to concatenate 2 lists. You can also use that on tapes. We can use snap to replace a character at a certain index with another character. So what's going on here is snap is going to take a list and an index and something to change at that index. So in particular, if I did this this is a common error people run into. If I did this is actually going to throw me an error because this is a list and this is actually a list, right? A tape is a list. So the elements of this list are not lists, they're characters, right? So we're trying, this is saying replace some element with a list. But what we actually have to do is just the character C, or like for clarity, we cast this to it, TD. So we're saying, let's go to index 10 in this list, replace whatever's there with C. And then instead of bats and mouse, just cats and mice. And recall what we learned about using cell notation to put something at the head of a list. We can do that with tapes as well. So here we have a cell of the character A and the tape B, C, D, E, F. So if we put those in a cell together and then we cast that to a tape again, then we get the tape A, B, C, D, E, F. That's pretty neat. That's pretty neat, right? Any questions on that so far? All right, so something else you can do is you can take any Hoon expression in wide form, put these brackets around it, and that'll render it as a tape. So this is saying the square root of the floating point 42 is 6.4807, blah, blah. So it's just these angle brackets like that. And you can also interpolate a tape within another tape with this syntax. So X is the tape above, and then we're interpolating X into this other tape. And then if you change X, then you can also interpolate that. So that's kind of a neat trick to, like, if you want to render like different kinds of text based on some logic, that's a cool trick. And you can combine even these angle brackets and these curly brackets to get some. Oh, let me paste these for you. And you can even combine these angle brackets and curly brackets. So let's set X to be the floating point square root of 42. And then we have this text that says the square root of 42 is X in angle brackets, then in curly brackets. And then we'll get the tape. The square root of 42 is 6.4807, blah, blah. So yeah, those are some neat tricks for working with text. We're basically at the end of the lesson. So are there any questions on anything that you guys just saw?
Yeah, it wasn't clear to me why you sometimes need to change from list to structure and back.
Sorry, list to structure and back.
Yeah.
Do you remember the example where you saw that?
I think way back. Like, I would scroll back your dojo to find out.
Okay. let's scroll the dojo. Tell me when you see something that.
When you were starting to, yeah, Limo.
So why did I sometimes need to use this limo?
Yeah.
And something? That's a good question. So what I found when testing some of these is that some of them, like length, for example, if I just do this, like, I didn't need to cast this argument to a list, right? It just worked. And I think that has to do with something about how length is built internally. If I did snap, for example, if I do snap and I don't cast this list, this structure to a list, this is going to fail. And I don't have a good explanation of why some of these fail and some of these require you to cast a tool list and some of them don't. But it's generally good practice if you have a list structured thing to cast it to a list just to make sure you don't get these errors. But yeah, some of them don't need you to do that. Like I think flop doesn't need you to do that. Yeah, flop doesn't need you to cast it beforehand. Length doesn't need you, but snap does. So it's a bit inconsistent. I wish this behavior was consistent, but basically it's good practice to always cast your list shape thing to a list.
Thank you. The other question is, what would be the easiest way to develop for those exercises? I've been basically just straight in the dojo, but I was wondering if it would be easier to, write something in the text editor and then paste in the dojo and then change.
Yeah, that's exactly what I would do. If you're once we're writing, like we're working on like more complex code expressions now, like multi-line things, right? So it may be a bit confusing to like try and write all that directly in the dojo. So it's a good idea to just pop open your text editor, like maybe VS Codium, but it can even be like Notepad or whatever. Just like draft your code in there and then copy paste it, see if it works, and then you can go back and change things. So yeah, that's what I would recommend.
Another thing, like I've been noticing it when writing in the dojo, and you try to write something that's not correct, the cursor will go back to a position where, like basically saying, until here, I was understanding you, but past here, it's nonsense.
Yeah, that's right.
So that's what it's doing, yeah?
Yeah, that's correct.
Okay. Thank you.
Yeah, but sometimes I can confuse you a little bit because like that's not exactly where the error was. Like the error might have been like some rune before that. But
Yeah, so it's interpreting syntax, not intention.
exactly. Yes.
Yeah.
Just saying the last point where the syntax stopped parsing.
Yeah.
Cool. Yeah. Any more questions? Since we're working with variable length structures, do we ever interact with pointers in Hoon? Or that's so there's no concept of a pointer in Hoon. If you'll follow like how we got to this point from the knock, we're just working with binary trees and like addresses of things in binary trees. So there's like no need for, in a sense, the abstraction of a pointer. Like we have addresses, right? But we don't like that doesn't need to be like we can also like store an address as data in a sense. So like in a sense, like Hoon and Knock are like simpler than C so that we don't need something like pointers, basically. Yeah, so it's not really hidden away, but it's just like it's a concept that doesn't map over from other languages, basically. Yeah, hopefully that made sense. Cool. Any more questions from anyone? We got 3 more minutes. And I have office hours after this as well at 1:15. So. All right, if there's no more questions, I'll stop the recording. Thanks everyone for being here. Hope you enjoyed.
Jack, one more question, please.
Oh yeah.
Sure. So your classes are following the curriculum in Hoon School in the website, yes?
Oh, actually, I am kind of charting a different path through everything. So
Okay.
if you follow what the docs on the website, a lot of the content will be the same, but doesn't go through everything in the same order that we're going to through. And I chose to do things this way because I'm hoping that it'll make more sense to people and be more learnable. So yeah, we're using a different order of the material, basically. Yeah.
Okay, thank you.
Yeah, so that might be a little confusing, but yeah. All right, so let's end the recording. Thank you everyone for being here.